question 6, we are told that at time t seconds, a particle is moving with an acceleration given by 5ti minus 15 2 to the half j. Now we know that when t is 0, the velocity of p is 20 meters per second, and we need to determine the speed when t is 4. So starting with the fact that we are given the acceleration, we know that we can integrate to get the velocity vector. So the velocity vector is the integral of 5ti minus 15t to the half j dt. So this is two integrals, one with respect to the I component and the other with respect to the j component. So if I integrate 5t, I get 5t squared over 2 plus a constant of integration, I'll call it c1, and that's the I component. And for the j component, it's plus minus 15 t to the 3 over 2 over 3 over 2 plus c2, that's the constant of integration for the j component, so that's j. We know that when t is 0, then v is simply 20i. So this means I can equate the 20i with the expression I obtained here with t being substituted with 0, which leads to c1i plus c2j. Now if I equate the I components, I see that c1 is 20, and if I equate the j component, I can see that there is no j on the left hand side, and therefore c2 must be 0. This means that we have a complete expression for the velocity vector, so v is 5t squared over 2 plus 20, that's the I component for the velocity, minus 10t to the 3 over 2j, the 15 times 2 over 3 simplified to a 10, and we are after the speed of p when t is 4. So when t is 4, I will be substituting into the expression for the velocity. I get 5 times 4 squared over 2 plus 20, that's the I component, minus 10 times 4 to the 3 over 2j, which gives me 60i minus 80j. This is the velocity vector. We are after the speed, and speed is the magnitude of the velocity. So speed can be found by doing 60 squared plus negative 80 squared and all square root, and this gives an answer of 100, and that's meters per second. Section 7, a rough plane is inclined to the horizontal at an angle alpha where tan alpha is 3 over 4. We've got a particle of mass m placed on the plane and then projected up a line of greatest slope. The coefficient of friction is mu. We are told that the particle moves up the plane with a constant deceleration of 4 over 5g, and we need to determine the value of mu. We certainly need a diagram here to see exactly what's happening. So this is the particle on the plane, the angle is alpha, the weight is mg, so I'm adding the forces here. I will be resolving the weight, so the vertical component, so the component vertically to the plane is mg cos alpha, and the component of the weight acting down the plane is mg sine alpha. Obviously, we've got a reaction, which I call R, and we are told that the particle is projected up the plane, so it's moving up the plane, and it's doing that with a constant deceleration of 4 over 5g. So I'm putting my arrows pointing upwards, and the acceleration is negative, so it's decreasing speed. And we obviously have friction. Friction is opposing motion, so it's acting down the plane. It's at its maximum value, F max, so it's mu r. So we've got all the forces acting here on a single diagram. In addition, we've been told that tan alpha is 3 over 4, so I could draw a right angle triangle that's 3 over 4. Obviously, the hypotenuse is 5, so we can conclude here that cos alpha is 4 over 5, and sine alpha must be 3 over 5. Remember, we're trying to determine the value of mu, so I will start by balancing out the perpendicular forces to the plane. So we have that R is equal to mg cos alpha, which takes me to 4 over 5 mg. mg. Then looking at the forces acting along the plane, now because the particle is moving up the plane, then I'm doing forces acting upwards, which is nothing, minus forces acting down the plane, which is mg sine alpha plus mu r, is equal to mass times acceleration, which is m times minus 4 over 5 g. I can now proceed. Sine alpha is 3 over 5, so I've got minus 3 over 5 mg minus mu times r, which is 4 over 5 mg, is equal to minus 4 over 5 mg. Notice that the mg is common throughout, so I can get rid of that, so the mg goes away, and also the 5 is a common denominator, so that can go away as well, which leads to minus 3 minus 4 mu is equal to negative 4, so 1 is 4 mu, and therefore we conclude that the coefficient of friction mu is a quarter. In part B, we are told that the particle comes to rest at the point A on the plane, and we need to determine whether it will remain at A, carefully justifying our answer. So let me quickly redraw the diagram of what's happening. So there it is. We've got the components of the weight acting perpendicular to the plane and down the plane. We've got the reaction here, and obviously we have a frictional force which is opposing motion, so the frictional force should be pointing upwards. Let's consider what's the maximum value that this frictional force can attain. So F max, we know it's given by mu r, which is a quarter, the value of mu we just found, times r, the reaction is mg cos alpha, which is 4 over 5 times mg. This is giving a value of 1 over 5 mg. Now let's look at the component of the weight acting down the plane, the mg sine alpha. So in our case, mg sine alpha is equal to 3 over 5 times mg, which we observe that this is greater than the maximum frictional force, so it's greater than F max, and therefore when we consume all of the available frictional force, there will be a resultant force acting down the plane, so this will be accelerating down the plane. We therefore conclude that A will accelerate down the plane, and it is imperative that you compare the component of the weight acting down the plane with F max in order to justify your conclusion here. In question 8, we've got a radio control boat placed on the surface of a pond. We're modeling this as a particle. Initially, it's moving due north with a speed of 0.6 meters per second, and the position vector at time t seconds is given by r meters. We are also told that when t is 15, the velocity is 10.5 I minus 0.9 j, and if the acceleration of the boat is constant, we need to show that this is 0.7 I minus 0.1 j meters per square second. Obviously, the keyword here is that the acceleration is constant, and therefore I can use the Suvad equations. We have been given that the initial velocity u is 0.6 meters per second because the boat is moving due north. So if I was to draw the velocity vector, it would be pointing upwards. Therefore, the horizontal component is 0 and the vertical component is 0.6 to the positive direction. We've got the Suvad equation, v is u plus at. So for v, I will be putting the 10.5 minus 0.9. For u, it's the 0.6 plus 15a because t is 15. This leads to 10.5 minus 1.5 is equal to 15a. So if I divide both sides by 15, I get 1 over 15 times 10.5 minus 1.5 is equal to the acceleration vector a. This turns out to be 0.7 I minus 0.1 j, and that's meters per square second. This is the acceleration vector. Notice that I had to give my answer in terms of I and j, so it's better to match the exact answer given here to score both marks. Otherwise, you will be penalized if you end up with an answer in a column vector form. In part B, we are asked to find r in terms of t. Well, we know that the position vector r is given by the initial position vector r naught plus ut plus a half at squared. We are told that initially we were at the origin, so we were at 0, 0. The initial velocity u is given to be 0.6 times t plus a half times the acceleration vector, which is 0.7 negative 0.1, and that's t squared. I will be giving my answer in terms of I and j. So the I component turns out to be 0.35 t squared I, and the j component turns out to be 0.6 t minus 0.05 t squared, and that's meters. In part C, we need to find the value of t when the boat is northeast of the origin. So I will start by drawing north, south, east, west. The position of the boat is northeast of the origin, so along this way here, so halfway through, which is at 45 degrees. This means that the vertical component and the horizontal component are the same, so I could put 1 and 1, which means that the position vector we just found is parallel to the vector 1, 1. This can be written as 0.35 t squared, 0.6 t minus 0.05 t squared. This is the position vector, is parallel to the vector 1, 1, so we are moving in the same direction, in other words. So 0.35 t squared over 0.6 t minus 0.05 t squared is equal to 1 over 1. I can cross multiply to get 0.35 t squared being equal to 0.6 t minus 0.05 t squared. I will collect everything on the left hand side, leading to 0.4 t squared minus 0.6 t is equal to 0. I will factor out the t, so t bracket 0.4 t minus 0.6 is equal to 0, which means that either t is 0 or 0.4 t minus 0.6 is 0. So I get 0.4 t is 0.6, which leads to t being 1.5, and obviously this is my answer, so I will be concluding 1.5 seconds. In D, we need to find the value of t when the boat is moving in a northeast direction. So the direction of motion stems out of the velocity vector. We know that v is u plus at, so I will start by finding an expression for the velocity at time t seconds. So the initial velocity was 0.6. The acceleration was found to be 0.7 negative 0.1. So this leads to the velocity vector being 0.7 t, 0.6 minus 0.1 t. And we know that this must be parallel to 1, 1 again, because I want it to be moving in a northeast direction. So we have 0.7 t over 0.6 minus 0.1 t is equal to 1 over 1. I will cross multiply to get 0.7 t is equal to 0.6 minus 0.1 t, leading to 0.8 t is 0.6, and therefore we get that t is 0.75, and this is also seconds. Remember, the time in this question is measured in seconds. In question 9, we've got a uniform ladder AB of length 2a and weight W, has its end at A on rough horizontal ground. The coefficient of friction between the ladder and the ground is 1/4, and the end B is resting against the smooth vertical wall. We've got a builder of weight 7W standing at the top of the ladder, and to stop the ladder from slipping, the assistant is applying a horizontal force of magnitude P to the ladder at A towards the wall, so pointing in this direction. Now the ladder rests in equilibrium in a vertical plane. The angle alpha with the horizontal ground satisfies that tan alpha is 5 over 2, and we are modeling the builder as a particle and the ladder as being uniform. We need to show that the reaction of the wall on the ladder at B has magnitude 3W, so it makes sense to start by adding the forces on the diagram. We've got the weight of the ladder, W, in the middle, so it's A to the left and A to the right, the distances. We've got the weight of the builder, 7W, at B, and we've got the reaction at the wall at B, so pointing away from the wall perpendicular to the wall. We've got reactions at A and other forces acting at A, but for the time being I'm not going to put those so that I'm not making the diagram too busy. We are being asked to find the magnitude of the reaction at B, show that it is 3W. So I will take moments about A. We can see that the weight W and the 7W are acting in a clockwise fashion about A. Remember, we're taking moments about A. And the reaction force at B is acting in an anti-clockwise fashion. So starting with the clockwise moments, we can see that the weight of W is acting at a distance of A cos alpha. So A cos alpha times W plus the 7W is acting at a distance of 2A cos alpha. So plus 2A cos alpha times 7W is equal to the anti-clockwise moment, which is acting at this distance here, which is 2A sine alpha. So 2A sine alpha times the reaction at B. We can see that the A is common throughout, so I can cancel this out. And I can also divide throughout by cos alpha. This will give me tan alpha, and the cos alpha over cos alpha will cancel out. So we can see that W plus 14W is equal to 2 tan alpha times the reaction at B. So the left hand side is obviously 15W and the right hand side is 2 times the tan alpha, which was given to be 5 over 2 times the reaction at B. So we get 15W is equal to 5RB, which means that the reaction at B is 3W as required. In part B, we are asked to find in terms of W the range of possible values of P for which the ladder remains in equilibrium. So I will be considering two different situations. So let's start with the diagram. I will add the forces once more. So we've got the weight in the middle, so the distances are A and A. We've got the weight of the builder 7W, the reaction at B, which is RB. We also have a reaction at A pointing upwards, and we've got the force provided by the assistant, but also frictional force. So we are modeling this as the ladder wanting to slip and go to the left, and therefore we've got a frictional force opposing this. I can equate the upward with the downward forces, and I get that the RA is equal to W plus 7W. So we get that RA is equal to AW. And we can now turn our attention to the horizontal forces. For the ladder to remain in equilibrium, this means that the forces to the left must be equal to the forces to the right. So we've got that RB is equal to P plus F. Remember, F is the frictional force. Now, RB, we have found this from part A to be 3W. So 3W is equal to P plus F, which means 3W minus P is equal to F. Now we can calculate independently the maximum frictional force. I'll call this F max, which is equal to mu RA. Well, mu has been given to be a quarter. RA has been found to be AW. So this is 2W. And we know for sure that the frictional force F must be less than or equal to F max. This means that 3W minus P is less than or equal to 2W, leading to W being less than or equal to P. So we have found the minimum value for P, and we will repeat this situation, modeling this as P being so large that the ladder is about to start moving up the wall, and therefore the friction will be pointing to the left. So this is what the diagram would look like in this case. So we have no friction pointing to the right, it's just the force P, and we've got friction pointing to the left, because remember, we are modeling this as the extreme case where P is such a big force that the ladder is about to start sliding up the wall, and therefore we've got friction opposing and pointing to the left. Once more, we can equate the horizontal forces, so RB plus F must be equal to P. So let me write this down. RB plus F is equal to P. Now we know that RB is 3W plus F is equal to P, which means that F is P minus 3W. And since F is less than or equal to F max, I can say that P minus 3W is less than or equal to F max, which is 2W, and therefore P is less than or equal to 5W, and therefore this can be nicely put together as W being less than or equal to P, which is less than or equal to 5W, the range of values for P for the ladder to remain in equilibrium. Now, often in practice, the builder's assistant will simply stand on the bottom of the ladder, and we need to explain briefly how this helps to stop the ladder from slipping. So we can say that considering moments about A shows that the reaction at B will remain the same. So if we take moments about A, then we can see that we eliminate the effect of the force applied by the builder's assistant, and the reaction at B will be the same. So by standing on the bottom of the ladder, we can see that this increases the reaction at A and therefore F max. So we are offering the maximum possible frictional force by standing on the bottom of the ladder. In question 10, we've got a boy throwing a stone with speed u meters per second from a point O at the top of a vertical cliff. We're 18 meters above ground. The stone hits the sea at point S, 36 meters at the horizontal distance from the foot of the cliff. We are told that the angle alpha satisfies that tan alpha is 3/4, and we are modeling the stone as a particle moving freely under gravity with g being 10 meters per square second. So let me highlight the fact that we are deviating from the standard approach of g being 9.8. We're using 10 here, and we need to find the value of u. Well, I will start with the triangle. Tan alpha is 3/4. It's a 3-4-5 triangle, which means that sine alpha is 3/5 and cos alpha is 4/5. I will then turn my attention to the initial velocity u at an angle alpha, which I will resolve into a horizontal component, which is u cos alpha, and a vertical component, which is u sine alpha. So I can come down and write that the component along the horizontal for the velocity is u cos alpha, and there is no acceleration along the horizontal, so the acceleration along the x direction is 0. And for the vertical, uy is u sine alpha, and ay, the acceleration in the vertical is -10 because we are throwing the stone upwards, so the gravity is pulling us down, so it's fighting motion. We can then use the fact that s, the displacement, is ut plus a half at squared. So for the horizontal, we can say that the horizontal displacement sx is simply u cos alpha times t, and therefore we have that 36 is 4/5 times ut, which leads to 45 being equal to ut. And for the vertical displacement sy is u sine alpha times t plus a half times -10 times t squared. Now the vertical displacement is -18 because we are 18 meters below the launching point, and this is equal to 3/5 times ut minus 5t squared. Now I will substitute the ut with 45, so this will take me to -18 being equal to 3/5 times 45 minus 5t squared, which means that 5t squared is equal to 27 plus 18. So we get that 5t squared is equal to 45. So t squared is 9, and therefore t is 3. Now, once we've got that t is 3 the time, I can go back to the 45 is equal to ut and simply say that 45 is 3u, and therefore we get that u is 15 meters per second. We are then asked to find the speed of the stone when it is 10.8 meters above sea level, giving our answer to two significant figures. So once more, let me put my resolved initial velocity u cos alpha and u sin alpha. So we are 10.8 meters above sea level, so somewhere there. So the distance above sea level, it's this one here, is 10.8, which means that the distance below the launching point can be found by doing 18 minus 10.8, which is 7.2. So I can use once more the vertical displacement. So the vertical displacement Sy is equal to minus 7.2 because we are 7.2 meters below the launching point, and this is equal to u sine alpha times t plus a half times minus 10 times t squared. So we get that minus 7.2 is equal to u, which is 15, sine alpha, which is 3 over 5, and t minus 5t squared. I will collect everything on the left hand side, which gives me 5t squared minus 9t minus 7.2 is equal to 0. And I will use a quadratic formula to solve and find the value for t. So we get that t is equal to minus negative 9 plus minus 9 squared minus 4 times 5 times minus 7.2 and all square rooted over 2a, which is 2 times 5. It's a good idea to show you our method. This gives me that t is 2.4 or t is equal to minus 0.6. Obviously the negative is rejected. We cannot have a negative time. So we've got the time to reach the particular position. So we can now proceed by reminding ourselves that the velocity is u plus at. So in the horizontal direction, the component of the velocity vx is simply u cos alpha, and this is equal to 15 times 4 over 5, which gives an answer of 12, whereas in the vertical direction, Vy is going to be u sine alpha plus the acceleration of negative 10 times t. So u is 15, sine alpha is 3 over 5, plus negative 10 times the value of t of 2.4. This gives an answer of negative 15. These are the components of the velocity. Remember, we're trying to find the speed, so I'm just going to use Pythagoras theorem. The speed is going to be 12 squared plus negative 15 squared and all square root, which gives an answer of 19 meters per second, correct to two significant figures. In part C, we are asked to suggest two improvements that could be made to the model. So the obvious one will be to use a more accurate value for G. We've been using 10, it could have been 9.8 or something even more accurate. The second is that by modeling the stone as a particle, this means that we are neglecting the dimensions of the stone. So maybe taking into account the dimensions of the stone would be an improvement to the model. And finally, we could also mention including air resistance. Any two of these would be enough to get the 2 points.